This is the lesson for the second day of multivariable calculus. And in this lesson, we're just going to discuss polar coordinates and a little bit of calculus with polar coordinates. So just like last time, this is something that had we had the entire year in AP Calculus BC last year, everybody would have seen a lot of, if not all of what we're going to discuss here today. However, since a lot of you didn't get to see that unit at the end of calculus, what I want to do is take a couple of minutes to go through 10.3, which is just really a review of stuff that you should have learned in pre-calculus on polar coordinates. And then really we're going to get into the calculus of polar coordinates primarily in section 10.4. So remember, this is stuff that for a couple of you may not have seen for a couple of years. So don't feel like if you're a little bit rusty on this, it's a big deal. I will say though, polar coordinates, very similar to with parametric equations, polar coordinates form the basis for, in 3 dimensions, what we're going to call cylindrical coordinates. So you really need to understand how polar coordinates are graphed and all of the relationships between the x's and the y's and the theta and the r. So make sure you understand these things because they're not going to go away. Cylindrical coordinates we don't use as commonly as we do with the parametric equations, but we are still going to use them quite a bit. Okay, so just as a quick review, when you graph in polar coordinates, you're always going to graph in the coordinate r theta, where r is just the distance from the pole, which is another word for the center point or the origin point on your graph. You also notice with that graph that we have those concentric circles there. Those concentric circles are representing the r values. So for each one of those circles, it's another r value of 1. So the first circle has r equals 1, second circle r equals 2, and so on. And then the theta value is measured counterclockwise about the pole. So for relationships between rectangular coordinates and polar coordinates, if we want an x coordinate, x is equal to r cosine theta, and we can derive these very easily just by doing a little bit of trigonometry. Y is r sine theta, and x squared plus y squared is equal to r squared. That's just the Pythagorean theorem. And then we can also get the relationship between the x and the y and the theta using tangent theta is equal to y over x. Okay, now, the thing that you have to be careful with here is when you're referencing coordinates in the polar coordinate system, there's an infinite number of ways for you to do that. And in order to reference it, when we do the r theta, typically what we do there is we try to use a positive r value and the smallest positive theta value, but we don't have to do it that way. So keep that in mind. So there's a couple of questions here where they're going to ask you about going back and forth between the coordinate systems. And I want you to pause the video and take a couple of minutes and just try to work through those questions. Okay, so for this first one, find the rectangular coordinates of this point. They gave you the polar coordinate point 6, 2 pi over 3. You can see on the graph over here that we've got this point already plotted, this point P up here. And you can see how the theta is measured. You can see how the r value is measured out away from that pole. Okay, so here is the result that I got. So x is r cosine theta. It's just a matter of knowing your unit circle values and knowing how to relate the x to the polar coordinates. And then the y is r sine theta, and we get 3 root 3. Okay, so for the second one, it said find the polar coordinates of the point P whose rectangular coordinates are given by this, -2, -2 root 3. Okay, so again, you can see that it's already been plotted for you. And this is one where it can start to get a little tricky with referencing the coordinates. So I tried to give you a few different options here. But the first thing is we need to know the r value because we need the coordinate to be in the form r theta. So I found the r value just doing the square root of x plus, or excuse me, square root of x squared plus y squared. And that gave me 4. And then I just did tangent theta is y over x. And I found that theta could be pi over 3. Clearly, we're in the third quadrant, so really I'm going to want to use the 4 pi over 3 value there, but the pi over 3 can come into play, and that's one of the things that you see here with my solution. So with my solution, I wrote it in a few ways. I did 4 pi over 3. But also, I could say, okay, well, it's pi over 3, but now I'm going to measure in the opposite direction. When I see a negative R value, that means instead of measuring out away from the pole in the direction of that angle, you go in the opposite direction. And then I also have 4 negative 2 pi over 3, and I can add 2 pi or subtract 2 pi over and over and over again. So there's really an infinite number of coordinates. But like I said, typically when you're going to write a solution for that, you're going to use a positive R value and the smallest positive theta value. Okay, so let's move on. And this is a little bit of calculus with polar equations. So this calculus that you see here is very, very similar to what you see in the parametric equations. So to get dy dx, now we have everything in terms of theta. So it's dy d theta divided by dx d theta. Now, what I will mention about this is that you don't want to try to memorize these formulas. What I want you to do is try to remember how this setup works. If you can remember this part of it, then all of this stuff is going to work itself out. So when I try to think about the slope using polar curves, I don't do this. I don't even think about that. All I do is dy d theta over dx d theta. If you want to try to memorize that messy formula, you can, but really that's all it is. It's just the derivative with respect to theta of r sine theta and the derivative with respect to theta of r cosine theta. So if you have your x and your y equations, just take the derivatives of those and then you don't have to worry about that whole mess. Okay, so in addition to that here, we've got the same idea with horizontal tangents and vertical tangents. It's just a matter of, does the numerator need to be 0? Does the denominator need to be 0? And we have the same idea with when we see a 0 over 0 as before. When we see a 0 over 0, that's typically going to indicate a cusp in our graph. Okay, so let's see. For polar curves, when we are graphing them, let me go through just really briefly how to do this on the calculator. So it says sketch the curve with the polar equation r is 2 cosine theta. So you can see what I have graphed there. And basically what I've done, I kind of knew what the result was, but what you can also do is you can just plug in theta values and you can get the corresponding r value for each theta value. So for example, when theta is equal to 0, I have the point, let's see, I would have r is equal to 2. So I can see that when theta is 0, r is equal to 2, and that's the first point. And I could do the same thing for example, pi over 2, pi over 3, any unit circle value, and then you can get enough points to graph the curve. From a calculator perspective, if I want to graph a polar curve, let me do 2 cosine theta here. So first thing I want to do is change the mode on my calculator into a polar mode. And in the polar mode, I want to graph 2 cosine theta. So you'll notice that within my y equals screen on the calculator, since I'm in polar mode, it's now going to default into this r equals because that's the standard form for a polar equation. And just like when we did the parametric equations on the calculator, I'm going to graph it using the value that, or excuse me, the setup that I see over here. And because the same information, depending on the theta value, I'm going to see the motion as, you know, whatever this is modeling goes through its shape. So as it creates that shape. So when I graph this, I want to look at my window. Typically, we're going to use 0 to 2 pi on these. It just depends on the constraints that you're given. Again, with the theta step, remember the calculator is just approximating this graph. It's not actually graphing the curve. So the smaller I make the theta step, the more points the calculator is going to graph and the more accurate it's going to be. The larger I make the theta step, the less accurate my graph's going to be. And if I make it too big, the graph will just, you know, kind of be useless. So when I graph this, I'm going to start with this on a standard window. So I'm going to do zoom 6. And when I do that, this is what it looks like. Now remember, this thing looked like a circle. So I actually am going to go through and I'm going to zoom in a little bit here. And when I zoom in, I'm just going to zoom in on the pole. And now you can see it still sort of looks like an ellipse, but also notice that I did 2 cycles of that graph. And the last thing I'm going to do is zoom square. So when I do zoom square, now you can see it is a circle, and you can see I'm doing 2 cycles of that circle. I started at the point 20, and I completed 2 counterclockwise revolutions of that circle. So very much like the parametric equations, where you can get a lot of information from what's happening with whatever's doing to create that path, typically motion, but whatever is happening there, you can get a lot of information depending on how many cycles, depending on which direction you're moving, and that kind of thing. Okay, so it also says find a Cartesian equation for the curve to verify your graph. Now this one's a little tricky. I want you to try that one out. Remember that we need to try to make either an X or a Y show up within our polar equation. And it also is helpful if you can make an R squared show up within your polar equation. So take a minute, try that out, and then we'll talk about the solution. Okay, so the first thing here, you may have gone through a lot of iterations on things that you tried, but if you multiply both sides of the equation by R, what that's going to do is that's going to allow me to now use my equivalencies that I know for R squared and for R cosine theta. I know what those are equivalent to in rectangular coordinates. So that will allow me to actually go through and rewrite this with the X's and the Y's. So R squared is X squared plus Y squared. 2R cosine theta becomes 2X. And now it's just a matter of isolating Y. And when I do that, here's what I end up with. Y squared is 2X minus X squared. Solving for Y gives me a plus or minus the square root of 2X minus X squared. So when I graph it in that form, if you graph it on the calculator in the function form, you'll see that you get the exact same graph as what we've created in the polar form. So not that difficult to do, but if you haven't seen that done before where we multiply by R, that might be something that you never thought of. It's one of those things where once you see it one time, now the next time you see it, you'll probably know what to do with it. Okay, so we also have some symmetry tests. When we have symmetries in our graph, there's some different ways we can identify them, and that's what this is showing. This is all in your book. You've got a couple homework questions on this. So it says, if the polar equation is unchanged when theta is replaced by negative theta, the curve is symmetric about the polar axis. And so what we're looking at there, when we say the polar axis, we're thinking about that horizontal axis. So that's the first one that they're talking about there. And if nothing changes, you can see that R theta is, reflected over to R negative theta. So when I see that happening, I know that I've got essentially symmetry over that polar axis or that horizontal axis. When I want symmetry over the vertical axis, what I'm trying to see is that R theta is equivalent to R pi minus theta. And you can see on this second graph how those points match up. So it's very similar to what we would do if we were dealing with the rectangular coordinate system. We would be looking at the X values. If we did a positive X and a negative X, in this case, the way to reference those points, we have to use a theta and a pi minus theta to get those corresponding points. And then the last one is symmetry about the pole, which is similar to symmetry about the origin. And you can see for this one, there's 2 ways that we can reference this. We can do R theta and negative R theta, but really in terms of a test, we typically do R theta and R pi plus theta, or pi plus theta, or theta plus pi. Okay, so on the next problem, what you are asked to do is use the symmetry test to confirm that this graph is symmetric about the X and the Y axis, and then you can graph it on your calculator and make sure that that actually makes sense. So we know it's symmetric, but go ahead and actually work through the symmetry arguments that are given above and make sure that this is true. Okay, so for the first one, you can see that if I have symmetry about the x-axis, that's symmetry about that horizontal axis. That means that cosine 2 theta should be equal to cosine of negative 2 theta. And what I did to verify that is I just went through and thought about a few unit circle values and just verify that that's in fact true. So you could use trig identities and prove that to be true, but that's not really the road I'm wanting you to go down here. That's not the path I want you to take. What I want you to do is just, think about it logically. Does that make sense? Check. If it doesn't make sense, then you've probably got something that's not equivalent and you don't have that symmetry. All right, so now for symmetry about the y-axis, same idea. What it said above was I have to replace my theta with a pi minus theta. So cosine 2 theta becomes cosine of 2 pi minus 2 theta. And again, easy way to verify, plug in a couple unit circle values and make sure that those are matching up. All right, let's move on. And the second section here is really where we get into a little bit more of the calculus applications of polar coordinates. So we're going to talk about area, just like we did in the last section of parametric equations. When we deal with area, it's a little bit different. And this is something that we didn't really get to talk about last year, but it still works in a similar way to how we find areas in the rectangular coordinate system. So to find an area, essentially what we're doing as we go around the pole, we're breaking our area into these sectors of area. And to find the area of each one of those sectors, it's essentially a piece of the circle. And you can see here where we've got pi r squared times theta over 2 pi. That's like the circle times the percentage of the circle. The theta over 2 pi is what gives me that sector. And that simplifies down into 1/2 r squared theta. So if I were to find one of those sectors, that's what it would be. Now, when I break this into a small incremental piece, now it becomes that differential piece of area is 1/2 r squared d theta. And then I'm just going to use an integral to add up all those pieces over whatever range of theta values that I've got. So I'm going to integrate from a to b 1/2 r squared d theta. So it's a little bit different in the derivation, but we're still doing the same general idea with the integral. We're adding up a bunch of small pieces of area. Instead of rectangles, now we're using sectors. Okay, so here's an example I want you to try. It says, find the area enclosed of the region in the first quadrant that is within the cardioid, r is equal to 1 minus cosine theta. So pause the video, set it up, and try to solve it out. If you get an integral that's messy, just go ahead and plug it into the calculator and get your solution from there. Okay, so here's what you should have come up with. 1/2 times the integral from 0 to pi over 2. Those are my theta values that constrain that shaded area we have there. And then my r value is, or my r equation is 1 minus cosine theta. So that's my r squared. And then I've got my d theta, and then just plug it into the calculator. Now, if you want to with these, it's kind of like the stuff with the parametric equations and the surface area. If you want to start messing around with trig identities and doing a bunch of stuff, a lot of times you can get exact solutions for these. I'm not necessarily going to ask you to get the exact solutions. One thing I do want to point out when you're doing these questions on your homework, if you're working through some of these problems and they're asking you for exact solutions and the integral starts to turn into a mess, don't worry about getting me the exact solution. Just type in the decimal equivalent. Wiley Plus is going to mark you incorrect on that question, but I'll still give you credit for that question. So don't feel like if you're not getting the exact solution, you're not going to get credit for it. I just want to make sure more than anything that you understand the setup, because I don't want you to get bogged down in dealing with trig identities and going through a bunch of stuff. I'd rather you really focus on the idea of the areas and getting when you're working with areas and you want to find your limits of integration. The main thing is to find the limits of integration, make sure you're actually thinking about the graph or looking at the graph, and then your boundaries, you're just going to go from obviously the lowest theta value to the highest theta value. When you start to go around theta is equal to 0, we're typically going to go from a negative theta value to a positive theta value when that comes into play. Okay, so for arc length, again, we have the same derivation that we were looking at before with arc length. The only difference now is the distances that we're using for the change in x and the change in y are a little bit different. So you can see that those, you know, like where we had dx and dy before, now we have dr, or the small change in the area, and then for that right triangle there, r d theta would be the other leg on that right triangle. So to get the length of the hypotenuse of that right triangle, which is that little piece of the arc length, we're going to end up doing the square root of dr squared plus r d theta, that quantity squared. And we can go through and we can algebraically manipulate that and come up with the arc length formula for polar coordinates. That one, again, I don't really recommend that you try to memorize all of these things, but arc length is one with polar coordinates that's a little bit harder to derive. You might not want to go through and try to derive that thing every time. After you've gone through and used the formula 3 or 4 times, you'll probably remember it anyway. But if you need to, that would be one that you might want to write down and say, okay, I really need to know this. All right, so there is an example here I want you to try. It says find the total arc length of the cardioid. R is equal to 1 plus cosine theta. So use your calculator to graph it if you need to, but take a couple of minutes, work through that, pause the video, and then when you're done, I will show you the solution. Okay, so here's what you should have come up with. Dr d theta is negative sine theta, so that's what I used in my setup. So for my overall length, remember we're going to use the integral from a to b of the square root of r squared plus dr d theta squared. So that's the setup that I used over here. And you can see that I've got my r squared, 1 plus cosine theta is squared, and then my dr d theta is squared, negative sine squared. And I just plugged this into the calculator. And again, if you really wanted to, this one has a nice round answer. So if you wanted to go through and do all of the algebra and trig involved with getting that exact solution, you can, but don't feel like it's necessary. Again, I don't want you to get bogged down in those details of solving the integral. I want you to focus on the big picture, which is the setup of these. All right, and then the last problem that I have for you here is finding the area of the region between 2 polar curves. So for this one, it says find the area of the region that's inside of the cardioid and outside of the circle. So again, pause the video, try to set it up and solve it out. And then once you've got that all done, unpause the video and I'll show you the solution. Okay, so here's what you should have come up with. Now, the big thing on this one is we've got some intersection points. So we have to make sure we know our limits of integration. And what I did was I just set the 2 equations equal to each other to figure out, okay, for what theta values do we have the same r value? And those should be the intersection points. And that happened at negative pi over 3 and pi over 3. And then it's just a matter of thinking about, okay, how am I doing the area? Well, what I'm doing is I'm taking that larger area, the area within the cardioid, and I'm taking away the area within the circle for that region. And so what I did was 1/2 of the outer radius squared minus the inner radius squared, or the outer curve squared minus the inner curve squared. It's kind of like what we do with rectangular coordinates and finding volumes when you have washers. It's kind of the similar type of setup. So I set that up, and again, I just plugged this into the calculator, got about 18.611. One thing I do want to point out, when you are looking for points of intersection, and this applies for polar coordinates and it really applies for parametric equations as well. Sometimes it's a little bit tricky. You might have curves that appear to intersect, but they're not what we call collision points. Collision points mean that they would basically be at the same point for the same theta value, or in a parametric form, they would be at the same xy coordinate at the same t value or the same time value. So a collision point and an intersection point are 2 different things when we're talking about polar coordinates and parametric equations. So be very careful with that. Just because the graphs are intersecting doesn't necessarily mean that that's happening at the same theta value or the same t value for the 2 different graphs that you're looking at. So just something to be aware of.